Hi, I'm Justin and I'll be talking about Lab 3 Part 1. As you can see, JA is connected to B and K is connected to 1 and JB is the complements of A and KB is connected to 1 and DC is the exclusive O of B and C. So as you can see from this table, 0, 0, 0. When JA is 0, KA is 1, it clears the set, so it's 0. If JB is 1, KB is 1, it toggles the B, and 0 becomes 1. The DC is basically 0, 0. For this, 0, 1, 1. So when J and K is both 1, it toggles this, it becomes 0. And when JB is 0, KB is 1, it clears the result and becomes 0. When DC is 1, C is 1. Okay, so now I'll express the sequence. It goes from 0, 0, 0 to 0, 1, 0 and to 1, 0, 1 to 1, 0, 0, 1, 1, 0 and 0, 0, 1. And for the transition step, it comes from 1, 1, 1 to 0, 0, 0 and 0, 1, 1 to 1, 0, 0. As you can see, it consists of a JK flip-flop, exclusive OR gate, and also a D flip-flop. So when I press an input to the switch which is connected to JA, before I press it is 0, 0, 0. After I press it, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, and go back to 0, 0, 0. Okay, in order to get the transition state, which is 1, 1, 1 to 0, 0, 0 and 0, 1, 1 to 1, 0, 0, basically we just connect the KA and KB to the switches and it will get the transition state. To get the transition state, the K and KB must connected to 0. In order to get back the steady state, the K and KB must connected to 1.
So I'll be doing part 2. I'll be doing this, a reverse 8-bit light chaser. So here we have this schematic diagram I have to designing the light chaser circuit. So here we are using 161 IC and 138. So here this is 161, this is 138. So I'm going to do a demonstration for this. But first let me explain this schematic diagram. So for the 161 IC, my master reset is connected to VCC, my VCC is connected to VCC, ground is connected to ground, and my CEP is connected to VCC. My CP is connected to the clock, which is this, and my Q0, Q1, and Q2 is connected to the A0, A1, A2 of the 138, which is here, and my CET and PE is both connected to the VCC here. So for the 138 IC, I have A0, A1, A2, which is what I mentioned above. The Q0, Q1, Q2 is connected to these three, and 4 and 5 for this E1 and E2 is connected both to the ground since it's active low, and E3 is connected to the VCC, and VCC is connected to the VCC, and ground is connected to the ground. So for the Y0 until Y7, they are all connected to the LED. So now I'm going to do a demonstration. Here we go. So now we change the clock module. So I'll make it smoother and faster. So here we have the light chaser. So light chaser is basically a sequence of light followed by the LED. So they will light up like this, turn on and off, sequential. So they will be like this, go one by one, and this is how light chaser is made. So I'll be doing part 2. So here there are 3 questions. I'll be performing part 2B. So now here we have the circuit, and here we have the truth table, and this is my schematic of this circuit. So now this is my truth table. I'll be doing 4 possible solutions. So I will be doing D is equals to 0, D is equals to D, D is equals to 1, and D is equals to D prime. So this is the 4 possible solutions that I'll be performing on this circuit later. So here I'll be testing out these 4 solutions here using this circuit to get this to get the outcome. So now here in the circuit, okay, so the first one I'll be doing this. I'll be pressing D, which means my D will be 1, and I should get an output of 0, which means my LED should not light up. So I have assigned this as A, this is my B, this is my C, and this is my D. So here for the first one, D is equals to 0. I need to press D. So when I press D, I should get an output of 0, which means the LED does not light up. Okay, so here when I press D, the LED does not light up. So D equals to 0 solution. Okay, so now I'll be going to D is equals to D. I'll be using this. When I press C, I should get an output of 0, which means the LED does not light up. So this A, B, C, my C is here. So I press. Yep, my LED does not light up too. So this is the second possible solution. And the third possible solution that I'll be doing is D is equals to 1. So for the LED to light up, I will press B. So here, as from my truth table, when I press B, I should get an output of 1, which means my LED will light up. Okay, so here you go, this is my B. Yep, my LED lights up. So for the last one, I'll be doing D is equals to D prime. So for my truth table, when I press B and C together, I will get an output of 1, which means my LED will light up. So this is my B and C. I press together. Yep, my LED lights up. So basically, this is the 4 possible solution that I have. So yeah.
Hi, I'm Phil, and today I'll be explaining part 3 of our lab 3 for DED. From this circuit here, we can obtain this K map after getting this Boolean expression. As you can see, there is a predicted static 1 hazard arising from this part here. The hazard occurs when B goes from 1 to 0. So B is connected to the clock, and that's how we get our circuit as shown here. As you can see, we have already obtained the static 1 hazard, as you can see here, where it's normally 1, but it occasionally dips to 0. After considering the hazard, you can see that we can add a prime implicant here to cover up the hazard. Okay, now that we have to eliminate the hazard, after we've added this new prime implicant here, which is AC, as you can see, we added an AC. We now need to use another gate, which is a triple input NAND gate. As you can see here, previously we had 2 inputs into 1 NAND gate, which allowed us to use 2 NAND gate, the dual input NAND gate. But now that we have added an AC here, we have to remove this in favor of a 3 input NAND gate. We now have a new 3 input NAND gate. Previously here we have our quad dual input NAND gate, and now we have added the 3 input NAND gate. As you can see here on the oscilloscope, you can see that the static 1 error has now been corrected. But now our output is 0 because of the NAND gate. Naturally, we can use an inverter to get the 1 back.